we wanted you to experience a doubling of gravity, a tripling, a quadrupling, etc., how big of a chamber would we actually want you to have to be inside of? So we can literally figure that out right here, mathematically derived, which is notice the force, centripetal, that's why it's got the sub C on there, equals the mass of the object multiplied by its velocity squared, and then divided by its radius. So let's go ahead and think of if you had to be inside of a chamber that was 10 meters in diameter, how fast would it have to rotate for you to experience essentially doubling the normal amount of force that you feel through the ground when it comes to gravity? So, well, force, remember, equals mass times acceleration. So the force you're feeling just standing there is going to be your body mass and multiplying that by the joys of that 9.81 for gravity. So if we just make life easy and say we've got we'll say we have a 100 kilogram person, so 220 pound person, so that's not exactly a small human, and we're going to have them experiencing normal gravity, 9.81 meters per second squared. Okay, so that's going to give us literally a total amount of force of 981 newtons. So if we have that initial of 981 newtons, okay, and we want to double it, so 981 times 2 equals 1962. So that's what we're looking for, is our FC equals 1962. And we know that we wanted to have a radius of 10 meters, and the mass is still 100. So how fast do we need to be rotating? How fast do we need to get that object rotating so you can feel double gravity? So with that formula, how are we going to set it up, guys? Nice. Now, Braden, that's not going to be in meters per second. That effectively is going to be, that's the rotation. So we're talking about, that's going to be the degrees per second. So 196.2 degrees per second. So think about it. This is going to be a chamber that you would literally be inside up against the wall of, and it would be rotating at almost 2 complete revolutions, sorry, 1 revolution every 2 seconds. And the radius is 10 meters, so it means 20 meters across. That thing is booking. So that's to experience double gravity. If we wanted to triple, quadruple, quintuple, we're just going to take that same initial mass, multiply it by whatever factor we want. Excuse me. So taking that 981 and multiplying it by whatever level of gravity we want to feel, and then that's going to give us an idea of how fast we'd have to have it rotating. So since I know Luke has admitted his fandom, what's the highest gravity force that Goku or any of those guys ever trained at that you can remember from the show? And anybody else that happened to ever watch Dragon Ball Z? Nice. So you go 500 times Earth gravity. So that means we would take that 981 and multiply it by 500, which is just Fruit Loops because your bones wouldn't even be able to handle it. They would just break. Literally, I think your skull would fracture just laying there. Which I'm pretty confident would. So we would take that 500 times 981, which is going to equal our FC. And so we would then take that number and divide it by 100. And then, yeah. Oh. And, oh my gosh, and then divide again by the radius. So we can have the degrees per second on the bottom. Holy crap. That's booking. That is booking. What do you guys come up with there for the answer? So I'm coming up with, hey, nice, Luke. Came with the same thing. So now you're talking about it would have to be rotating at a speed of, yeah, we're talking about over almost getting closer to 1.5 revolutions per second. So just a wee tad faster. Oh, I think we forgot a zero on the end there. I think it would actually be 4,905. So, just a little over 10 revolutions per second. Mm. Mm. I love science. So, angular acceleration. Let's go ahead and walk through an example here. So, if we have we're looking at having an initial torque. This torque is going to be equal to our angular inertia multiplied by the acceleration that the object is going to encounter. Okay. So let's say, actually, let's have a little fun. How many of you guys have, like, it's not a is it a merry-go-round? The thing that you'll find at like a park where, like, as a kid, you could, run alongside it to get it up to speed, and then, okay, cool. So with that merry-go-round, it's going to have its own mass and its own radius. So that's going to be the k squared. What do you think the mass of a typical merry-go-round would be? What do you think the mass of a typical merry-go-round would be? Whew. We got 500 kg and 120. Let's go with 120 for the first one, but then Braden will go through the second time with your 500 kilograms, meaning that we've got effectively a 380 kilograms of people on top of it, okay? So I'm gonna say the radius for a lot of those merry-go-rounds is maybe 1 meter, maybe, just so it makes our math pretty easy. So our initial inertia is just going to be equal to 120 times 1 squared. So we literally just have an angular inertia of 120. Okay, now we want to, let's say we want to accelerate it up to what, because it's going to be starting at 0 degrees per second. What rotational speed do we want to get it up to? How fast do we want this merry-go-round to be rotating? Okay, 10 miles an hour, which is a little more difficult to think of when we're rotating. So it's more like revolutions per second, but you could technically do that if you think about the displacement from the end, which is probably, man, you guys don't make math easy on me, do you? I like it. Yeah, let's say we're trying to get it up to probably like 2 or 3 no, it might be closer to, 400 degrees per second. And I still might be inaccurate there, but we'll go with that just to make life easy. So we're going to try to get it up to 400 degrees per second. Okay. So if we're going to get up to that, now we have to ask ourselves, how quickly do we want to get there? How quickly do you guys want to get up to that speed? Three seconds. Awesome. So think of it, guys. If you're a kid and you're running alongside the merry-go-round, pushing it to get it up to speed, we're taking 3 seconds to run and get it up to speed. So we're going to have more time to get it to essentially accelerate it. So we're not going to have to produce as much torque. Whereas if we try to get it to that speed really quickly, that's what's going to be really difficult. So what we're going to have is a grand total of the initial formula is going to end up being 120 multiplied by, because remember guys, that was our rotational inertia, multiplied by 400 divided by 3, which is going to give you 133 degrees per second squared. And that is going to be equal to the torque required to get it to that speed. So that's how we would solve for the torque. Now, if you were to do the same thing, only with the previous idea of it being a 500 kilogram merry-go-round, which means it's literally weighing 1,100 pounds. So just a little heavy. You would have to be going obviously much, much faster. So you'd have to now, or the amount, not going faster, you would have to be producing a lot more torque. So instead of that 120, now we'd be looking at 500 times that 133.33 degrees per second squared if we happen to do it with the same acceleration. Now, the funny thing is, you could do it in the exact same amount of torque required that you did effectively, or the same level of torque required previously. You could just leg it out to be even longer of a period of time that you are going to try to get it to go up to that speed with. So our angular degrees per second would be much lower because we aren't trying to accelerate it as rapidly up to that speed. Does that make sense of how we can look at angular acceleration through understanding torques? Now, when you think of your project, how is this important? You guys look at your projects. How is this important?
Like I was thinking, like we have serving a volleyball, so like you have to create enough torque to be able to, when you apply, I guess, force to the ball to make it go where you want. Would that be applicable? I guess.
Yeah, because guys, you've got to accelerate all of those joints, or you have to accelerate along those joints. And so you're going to have the mass of whatever the object you're moving is. You're going to have the radius of that area. And from there, you're going to go ahead and be able to derive what's effectively going on. Right. So now I just put a link up in the chat. It's the exrx.net /kinesiology/segments. So go ahead and follow the link that I put up. So hopefully it hasn't corrupted yet. Sweet. So here's what you guys can go ahead and do with this. And this is specifically whenever you're looking at your project. So what you can go ahead and do is literally go through and figure out effectively how much different segments of the body are going to be weighing and then from there you can figure out literally how much would the leg weigh, how much would the arm weigh, how much would the shoulder weigh. And if you know what percentage of the body weight, and thanks to that anthropometrics lab, when you're going to measure literally the length of different areas of the body, you can then figure out, okay, there's my rotational inertia that I have to overcome, which does not include the extra load. Now, the segmental center of gravity is important because if you know the length of it, then effectively where the most of the weight is going to be. So hence, if we're talking about just the head and the neck, notice it's not at 50% of where the neck begins to the top of the head. It's gonna be a little bit above at 55 because obviously you've got much more skull, and unless you've got a gizzard, you don't have a lot of extra weight sitting lower on your chin. And then whenever we're looking at things like the arm, the upper arm's center of mass, just like the forearm's center of mass, they're closer to the actual body because you've got more weight in your upper arm than your lower arm. The bottom part of your forearm is going to be bigger than the upper part of your forearm. Whereas the hand is going to be slightly different thanks to the joys of having those fingers. But the goal is that you guys are going to go through, you can use this reference, and there's much, I noticed they're alluding to Plegenhoff 83, Deliva 96, Zatsiorsky's adjustments to their initial work, which I think the Zatsiorsky's is a good one for if you guys are looking for examples. So, any questions through there? What you can look at, how you can break that down, and give you an idea when you're going through and doing the rotational work. Good, Luke. All right. So, on through the joys of our angular inertia. Let's have a little fun with an angular momentum, okay? So, angular momentum, here's our formula. Our angular momentum, h, equals our mass times our radius squared multiplied by our rotational velocity, okay? So, go ahead, guys, and give me an initial height, because that's going to be our radius. Well, half of it is going to be our radius for a person, and give us an initial mass. Thank you, guys. My computer's, oh God. I just saw the chat and then it disappeared because my computer is running glacially slow. But I was sure there's a number there. So somebody want to unmute themselves and let me know what that number was.
Just 1 second. I'm running that height calculation again. I accidentally typed the wrong number in, but the weight that Raylan put in was 80 kilograms.
Sounds good.
And then, let's see, run the conversion really quick. And then 21 point, no, wait, hang on, no. Sorry, my brain's not working this morning.
It's okay, it's okay. You can just give me the height in meters.
Okay, yeah, it's going to be 1.778 meters, about 5'10".
Okay, so if we've got 1.778 meters, our radius is effectively going to be half of that. So now we're talking about what would be 889. So 0.889. So there's a radius. Okay. And so from there, we need to, we're going to have this person do a flip. So they're starting off standing, straight up, as tall as they can be. And they're going to have an initial rotation of, let's say it's going to be a grand total of, and that's going to be that lowercase looking w, which is really an omega, a lowercase omega, but my handwriting is not great. It's going to be 30 degrees per second. Okay. Now, we'll say that they'll be in the air for a grand total of 1 second. So if they stay rotating at that 30 degrees per second for the entire time, how's that going to go for them? They're going to go from being straight up and down to rotating 30 degrees. So they're just going to, So we probably need to rotate a little bit faster. And remember, once we start that angular momentum, that rotation, what we can do is we can change the radius. So we can decrease the radius, aka we can tuck into a tighter ball. So we just need to set up our math to figure that our initial and our final have to be the same. So we need to effectively get this rotational velocity up to how many degrees per second? I can't see the chat, so if you guys put something up there, I don't know what's going on.
Be 360, correct?
Yes, it has to be more than 360 degrees because we're starting at 30. So if we finish at 360, we probably still weren't, because we're going to go faster, but we're probably still not going to get fast enough to get all the way around and land on our feet. So if you figure if we start at 30, we probably need to get up to, like by the time we're coming back around to the ground, closer to twice. So instead of 720 degrees, it's going to be about 690 degrees. Okay. So our H sub 1 equals 80 times 0.889 times 30. Our H2 then has to equal, well, we're still 80 kilograms, unless you're vomiting, peeing yourself or something else while you're flipping, which hopefully you aren't. That's going to stay the same. But we know we now want this rotational velocity to be about 690 degrees per second. So we've got to now make this K much smaller. And it's going to be, remember, squared. Because, remember, H1 is going to equal H2, actually. Awesome, guys. Yeah, now I see what you guys are putting up there. I'm sorry. It's the joys of looking at these things. Okay. So H1 equals H2. So effectively, we could write it out as 80 times 0.889 squared times 30 equals 80 times K2 squared times 690. So if we're looking at it like that, okay, we're going to have 80 on both sides. We can just get rid of those. Oh my God, I take up too much space. We're going to get rid of those 80s. We're then going to have 690, and then we're going to have 30. Then we're going to have our K squared, you don't know what that is yet, and we're going to have 0.889 squared. So we're going to divide both sides by 690. Okay, so then we have 0.889 squared times 30 divided by 690 equals K squared. So what we would then go ahead and do is take the square root of both sides, because that's going to leave us with the final equation of K equals the square root of 0.889 squared times 30 over 690. So how crazy tight of a ball would we have to get in if we started rotating that slowly? Take your time, guys. Let me know what you guys come up with, and then let me know if you have questions over what we just went through. Whew. 0.185. And Rowland, that looks like it's probably going to be accurate. Now, here's the thing. When you get them to be, so that means they would effectively be, you know, that's the radius. So the diameter of them in that ball tucking would be a grand total of double that number. So you'd end up with essentially 0.39, or sorry, no, 0.37 meters. And 0.37 meters is a little over 1.5 feet. Don't know how feasible that's going to be for a human being to tuck that tightly. But that's because they would have to set with a higher velocity. And the other big key is when people are actually trying to tuck, that's why they extend up nice and tall, because that's increasing my initial radius. So that way I have a greater potential to go ahead and decrease in size and rotation. Now, so just made up momentum and looked for the shrink in radius we would need to land. Yes, yeah, that's exactly what we did, Braden. We effectively figured out if you started at X radius, so that's half of their height when they're just standing, with a 80 kilogram person, that's a grand total of about 5'10". And so that's not saying they're going to set with their arms at all. So they're just jumping plane, and they're only starting rotating backwards at 30 degrees per second, which means they literally did not start off rotating with a high enough velocity to help them get around. That's why if you see somebody do a standing backflip, a lot of it comes down to how they set initially. And so it's going to seem random, but it's not. How many of you guys are familiar with the actor Jason Statham? Wow. Nobody's really familiar with that. None of you guys have seen Sean Hobbs. None of you guys have seen, okay. So we at least got one. Now,
Because I couldn't type fast enough, sorry.
well, it's okay, Luke. Now the key is, do you guys know what he did before he was an actor? So, fun fact, he was actually a diver, like an Olympic level diver. So this is Jason Statham in 1990. Notice he still has hair. And the funny thing is, I think he's probably in better shape now than he was then. Watch how tight of a ball he's going to get into when he starts rotating to go and flip through. That's where you see the slow down in rotation and then the speeding up of rotation, because they literally are going from having a larger diameter to a smaller diameter. So watch again. See how they go? They set nice and high, close nice and tight, and then open to slow down that rotation right when they're trying to obviously dive into the water.
What do the judges look for in diving?
Did you do it correctly? Were you under control? Did you effectively make a smaller splash? Because if you watch them really carefully, you see them cut through the water tension and pull themselves into the water really aggressively. So, congratulations. You've learned something new today. Nice, Zach. So, but that's why we're going to care about angular momentum, because it's actually going to be a big component of things like diving, things like gymnastics. And that's why you see athletes obviously naturally tucking in a tighter ball, because that's going to allow them to rotate at higher speed. Same thing's going to be true with ice skaters. Whenever they're going to try to rotate faster, they're going to bring themselves into a tighter position. And even the same thing could be said about doing something like a spin move when you're playing the sport of basketball. The tighter you make your radius, the more you pull your body in through your center, your midline, you're faster, you're going to be able to rotate. So hence, if you try to rotate with your arms out nice and wide, it's going to naturally slow you down. So since the height and weight are similar to my own, I know how much to tuck my body to a flip. Yeah, if you guys want to learn how to do a back tuck, I can teach you guys how. The key is, there's a number of technique things you need to focus on, and then if you don't really care much if you live or die, it makes it a lot easier to do. I'm actually kind of joking on that last part. Like the first time you throw a backflip, your brain will typically tell you that this is crazy. Why are you trying this? This is how you can, take yourself out if you're not careful. So you learn with time how to overcome that. But really, it's a lot of speed and timing. So any other questions over these components or anything else with rotational physics you guys want me to go ahead and spend some more time on introducing you guys to it and having some more conversations about it? Okay, so the last thing we're going to go ahead and touch on, guys, we're just going to do a leverage formula, and then we'll call it for the day. Okay, so, and this is going to be the exact same thing you're literally going to be doing with your own project. Okay, so if we have equilibrium in versus movement, meaning we're staying in the same position, we're going to be producing as much force on the way up for our muscles as we're feeling coming down through our limb. Okay, so for example, we have a wonderful bluegrass sanitizing wipes container. It feels relatively full. I don't see a weight on it. Figure this is going to be about, we'll say it's 2 kilograms, just so I don't seem too incredibly soft. Okay, our effort times our effort arm equals our resistance times our resistance arm. So when I'm holding my arm out and straight in front of me, my effort is coming from the anterior deltoid. Okay, so the fulcrum is my shoulder joint. The insertion, which is going to be in my humerus, that's where I'm lifting from when it comes to my deltoid. Okay, so the effort, which we don't know yet, we are going to solve for, okay, is going to be equal to the length of that limb, or sorry, the length that we're going to have. So given the length of my arms, we're going to figure that's probably going to be we're going to say it's going to be about 0.2 meters. Okay, so the effort times the effort arm equals our resistance times our resistance arm. So times the effort, which we don't have. Now, the resistance is not just going to be the resistance of that bottle of wipes, and we're going to say my arm is about 1 meter long, so I really do have pretty long arms. So the resistance there is going to be equal to 2 kilograms. Now, we need to convert this into a force times 9.81 meters per second squared. Multiply that by 1 meter. What else do I naturally have to hold up whenever I have my arm out to the side? What's the other weight that I'm lifting? And I'm sorry, I can't see the chat again because our stuff. Okay, cool, I can see it now. Okay, what else am I having to hold up whenever I have my arm up like that? What other weight am I having to overcome? Well, we have the gravitational effect, which we factored into of what's going on with this guy, but what's the other weight that we're having to overcome? Exactly, Zach, the weight of the arm itself. So the arm is going to have its own center of mass, which instead of being that full 1 meter away at the end of my hand, it's going to be, remember from what we just looked at, it's going to be like 45% of the length of the arm. And if we say the arm is 1 meter in length, well, now we're going to have plus 0.45 meters multiplied by, and that's again going to have to be factored by gravity, which is going to be multiplied by the weight of my arm. And the arm itself is usually going to be somewhere like 5 to maybe 10% of body mass. We'll say it's 7%. I weigh about 95 kilos. So altogether, you'd have 95 times 0.07, which would give us the total mass of the arm. So we're just going to say it's going to be 6.25 kilograms just to make life easy on ourselves, guys. I know that's not correct, but we're just putting it up there because it gives us an idea, and you guys will always get everything you need to solve this. So now we have to run through and do our math, okay? So we're going to end up with effectively 16, or sorry, that would be 19.62, okay, Newton meters for the first part, plus 6.25 times 9.81 times 0.45 to give us our next effectual torque that's pulling us downward. And how much would that be, guys? How much would that be? Of 6.25 times 9.81 times 0.45.
$27.59.
27.59?
Yeah.
Thank you. So we would then go ahead and sum those together. So we're going to end up with 1, 2, 7, and well, cool. 47.2 Newton meters equals our effort times 0.2. So now divide both sides by 0.2. So our effort, just holding up a small, 4.4 pound can of wipes is going to require the deltoid itself. Nice, is going to require the deltoid itself to produce how many Newton meters of vertical force? No. Notice it's divided by 0.2, Zach.
My bad.
Divide by 2. So that means it's going to be, 236.05 Newton meters by the deltoid. And here's the other fact that we haven't even looked for. That's just the vertical force component. The deltoid, if you guys notice, it pulls in a pretty tight angle. So the force vector going upwards is the one we're using to lift, but it's actually pulling a lot of just keeping the shoulder in the socket whenever you're lifting yourself up. So we're going to learn your muscles, the actual muscle themselves, when they're shortening, they are incredibly strong. The key is we don't happen to have a whole lot of obvious, the strength is there. The problem is our leverage is so poor. So any questions from the things we've gone through today, guys? Otherwise, we are all wrapped up and you guys should have yourself a great day. You guys good? Questions, comments, concerns?